Hello everyone, today we are going to talk about the spherical harmonics in quantum mechanics. These are special functions that help us get the wave function for a particle in an atom. So let's start. So our Schrödinger equation in the Cartesian coordinate system for a particle in a 3D space looks like this. So we have psi plus v psi equals e psi, okay? And here's the Laplacian operator. And this is a very nice equation. We can solve it for a bunch of simple cases, like a particle in a 3D box. In fact, I actually solved it for a particle in a 3D box in one of my previous videos titled Unfold Degeneracy of a particle in a 3D box. I recommend watching that video before this video because a lot of the concepts I'll be using should transfer over to our new coordinate system that we will be dealing with. So here's our Schrödinger equation for in the Cartesian coordinate system. However, what we want to achieve in this video is that we want to change this coordinate system to the spherical coordinate system. So why are we doing this? So why do we want to change? That's such a very nice equation. We want to change the coordinates to a new system. So why are we doing that? Well, I want to motivate that concept. So first of all, a recap of the Cartesian coordinate system. So this is the one that we all learned in like 5th grade. So you have the z-axis, you have the x-axis, then you have the y-axis. It's very nice. But what if we have some planet orbiting around the sun? We can use the Cartesian system to model this, but it becomes pretty cumbersome to work with. We can instead, though, adopt the new system, the polar coordinate system in 2 dimensions, where we have some radius. So the radius r is just the distance between the Earth and the sun, and then as the Earth moves around the circular orbit, it traces some angle theta. And our system is just r and theta. So it makes more sense to change our coordinate system for the polar, for the movement of the Earth around the sun. Similarly, we instead want to use the spherical coordinate system for a hydrogen atom. This is because I have the nucleus here, which is just a proton, and I have an electron. Okay, and the potential actually only depends on the radius. It's purely radial. Like if I have an electron that moves a bit to the left, as long as the radius is the same, the distance between the electron and the proton is the same, our potential doesn't change at all. So it makes more sense to adopt the spherical coordinate system, r, theta, and phi. And that's just the same as the polar system, but in 3 dimensions. So let's just write out what that looks like. So x, this is the Cartesian one, and so the polar system I have some radius r. This is some angle theta, and then I have some angle phi. I move around here. You guys should already be familiar with that concept before going into this video. So, we are going to change our coordinate system into the spherical coordinate system. So let's start. So our Laplacian for the spherical coordinate system is 1 over r squared partial over partial r times r squared partial over partial r plus 1 over r squared sine theta partial over partial theta of sine theta partial psi over partial theta plus, we're running out of space right now, plus 1 over r squared sine squared theta of partial psi over partial phi, secondary partial of it actually. Oops, yeah, that's actually just it. Oops, oh my gosh. I made a mistake. These sides shouldn't be here. Completely ignore those sides. Ignore those. Okay, so here is the Laplacian for our spherical coordinate system. Okay, very nice. So the Laplacian for our spherical coordinate system. So what we do now is we plug this Laplacian into our Schrödinger equation, and that gives us this. Let's move this up to the front. Again, no, there's no side here. I made a mistake. Ignore those sides completely. So you plug this into the Schrödinger equation to get minus h squared over 2m times 1 over r squared partial over partial r times r squared. Now we have the sign there. It's the Schrödinger equation, not the Laplacian anymore. Now r squared is sine theta partial theta of sine of theta partial psi over partial theta plus 1 over r squared sine squared theta partial second partial of psi with respect to phi plus v psi equals e psi. Okay, now you guys may be asking, whoa, how does this format simplify things? How? And I get those queries there, because this is supposed to simplify things, but it seems as if it makes it more complex. Now, what we're doing here is we're doing a bit of a trade-off, kind of. So for the Cartesian system, just setting up our problem is very simple, but to actually solve our problem in the Cartesian system is very hard. The problem being the wave function for a hydrogen atom. But for the spherical coordinate system, setting up our problem is pretty hard. But then actually solving it is much more easier compared to if we were using the Cartesian system. So what we're doing here is we're just making it hard at the start, so that later it's going to be easier for us. Now in this video itself, we're not going to actually solve the Schrödinger equation for anything. All we're doing here is we are setting up the format for when we do solve the wave function for a hydrogen atom, like in the near future. So I'm going to be alluding to that many times in this video, because that's why I'm making this. This is a prerequisite for the amazing hydrogen atom case. So yeah, let's get back on topic. So now what we do here is we take psi, it's a function of r, theta, and phi, and we separate that into two parts, into a purely radial function and a purely angular function. Now you guys may be wondering, whoa, why do we separate this angular function into an extra two parts? Well, this is because that for the hydrogen atom, just all atoms in general, the potential, well, I think that's a bit of a, well, actually, I think so. Yeah, for all atoms in general, the potential purely depends on the radius. So our R function will depend on our potential, since our potential is radial. But our angular function is not going to depend on our potential, since our potential does not depend on theta nor phi. This means that for different potentials, our angular function will remain stagnant, but our radial function will not. So when we actually solve the Schrödinger equation for atoms, what we actually care about is this radial part. We actually solve the Schrödinger equation for this radial function instead, and when we are done, we just stack on the angular function to that function to obtain our general function. So it's analogous to the wave function, the time-dependent wave function. So assuming our potential depends purely on space, psi of x t can be separated into psi of x and then psi of t. Okay, and psi of t is just one value, right? Psi of t is just e to the minus I e t over h bar. So psi of t is the same for all cases, for all these different potentials that are purely spatial, remind you of that. Because our potential is time independent. So our psi of t will change depending on our potential. However, our actual spatial wave function will. That's why we solve the Schrödinger equation for the wave function, and for the spatial wave function, and then we tack on that time wiggle factor term to obtain our general wave function as dependent on time. That's the same thing that we're doing here. We're interested in r of small r, and all we do after is we just tack on the angular term to get our general wave function. Okay. Now this r of r, this radial term, it's called the radial wave function. That's what we call it, the radial wave function. And this y of theta phi, it's the angular term. It's also called the spherical harmonics. So what we want to achieve in this video is we want to solve for these spherical harmonics r. Because remember, they're going to be constant, like this wiggle factor term. It's going to be constant for all of our potentials. So we really want to find out what that constant is, so that once we do that, all we care about is the radial function, and then we can just stack on that harmonic onto there to get our general wave function. So that's what our objective is. So if you guys are ever wondering why we're doing something in this video, like the main idea is just to find out what this y theta phi term is going to be. Okay, so now what we do here is we just plug this whole thing into our Schrödinger equation. We substitute psi for the radial term in the angular term. This gives us minus h bar squared over 2m times 1 over r squared partial over partial r of r squared partial over partial r of ry plus 1 over r squared sine theta partial over partial theta of sine theta partial over partial theta ry again plus 1 over r squared sine squared theta partial over partial phi secondary actually ry, then plus our potential, which is going to be the radial potential, because again we're doing this so that we can solve the hydrogenic orbitals in the future. So we're using v of r, and then so we have ry that equals ery. So yeah, I really want to stress this, guys. If our potential does not purely depend on the radius, well then these become a bit more complicated. But for atoms, the potential, thankfully, is just radial. That's how the universe works, because it's really nice to us physicists. It only cares about the radius. So that's why we are doing v of r here. Okay. So what we can do now is that note that y over here is a constant relative to this partial over partial r derivative. So you can move y to the front here. So you can move y to the front. Same thing for the r's here. It's a constant once evaluated with this theta and phi derivative. So we can move the r's to the front. So these r's go away. What we can do now is we can divide both sides by r and this y. Not e, that was an accident. E is still here, guys, by the way. We just divide both sides by r and y. So doing that, well, you divide this by r. Where's r? Oh, r is not anywhere here, so this has an 1 over r term, and this y goes away. This r goes away. This r goes away. You have 1 over y terms picked up on these two terms, and now we have minus h bar squared over 2m times 1 over r, or 1 over small r squared, times 1 over big R, partial over partial r, times r squared partial big R over partial small r, plus 1 over y, plus 1 over y, 1 over small r squared sine theta partial over partial theta of sine theta partial big Y theta, and then plus 1 over y 1 over r squared sine squared theta partial of big Y v plus our potential v of r equals E. Alright. Now it's a bit hard to see. It's a very long expression. I don't have bigger paper. Well, I don't have a bigger phone. That's what matters. But this is the entire thing. Okay. So now what can we do? Well, now it helps to multiply both sides by minus 2m r squared over h bar squared. And this is going to simplify things out a lot. So you multiply this by minus 2m r squared over h bar squared, minus 2m r squared over h bar squared, and that gives us, well, this goes away, this goes away, this goes away too, these minuses go away, but now we have the r squared that's picked up here. The r squared jumps to this part, cross cancels out with this r to give us 1. And the r squared jumps here, takes this one out. R squared jumps here, takes this one out too. Then we can factor this one y term over here. And now we have 1 over r. Here, let's move this up even more. So now what we have is 1 over 1 over r partial over partial r. Oh, also what I want to do is we are going to subtract this part. We'll just we want to add this term to both sides, and you're going to see that you do that right now. So I have 1 over r partial r. I have r squared partial big R, little r, and now what we do is we have plus VR. This is all addition, right? So we can just move this. Like, we've already distributed this thing in, so we can just move this VR like right over here because we're just all doing addition. It's commutative. So I have v plus, oops, not plus v just yet. So we have minus 2m r squared over h bar squared times v of r, right? And also our energy is minus 2m r squared over h bar squared times e. So what we can do is we can factor out this 2m r squared over h bar squared term, well, the minus 2m r squared over h bar squared term, to actually give us minus of 2m r squared over h bar squared times v of r minus e. The e is minus, and you can see that this works, right? Since if you just do this, put it on here, comes a positive, and here is a positive once we add this to this side to give us 0, by the way. And then now what we can do is we can factor out this 1 over y. I'm going to put brackets here for reasons that I'm going to talk about in the future. So now plus 1 over y times brackets of 1. So we're just factoring out this 1 over y term, by the way. So 1 over y times 1 over sine of theta partial over partial theta of sine theta partial y over partial theta. Running out of space here. Plus, yeah. I'm going to put this term over here. So plus 1 over y. So not 1 over y. That's already factored out. Plus 1 over sine theta, sine squared theta, second partial of this phi. Okay, and curly brackets here. So now we have this. Okay. And this entire thing equals 0. So we subtracted this term, the energy term, scaled with that concept variable thing. We added that to both sides since it was a negative, and we got 0. Okay, so I want to make a very nice argument here. So let's call this entire thing the radial term, because everything here depends on r, or it's either dependent on r or it's a constant. Let's call this part the angular term, since everything here depends on the angles or it's just a constant. Okay, so this is a very weird thing here. You might not notice it's pretty subtle, but this is very weird. Since we have, okay, this purely radial term plus another purely angular term equals 0. So so we can subtract both sides by the angular term. Let's call the radial term f of r. Again, f of r just being this entire thing. Let's call this angular term f of theta and phi. And so we can say, okay, this whole thing equals, we just subtract all this, because we just subtract this by both sides. We get f of r equals minus f of y, not f of y, sorry, f of theta phi. Okay, and this is very weird. And so remember, looks like this paper is showing here, so let's do that. So remember, this is purely dependent on r, and this is purely dependent on theta and phi. So how can a function that is purely dependent on the radius be equal to a function that's purely dependent on theta and phi? Once you put on a negative there, that doesn't make any sense, right? Since, for example, I'm running out of paper, guys, so let me just go on to the next page. So here I have f of r, that's equal to minus f of theta and phi. How is that possible? Because, like, say, this is not what f of r is. I'm just giving you guys an example. Like, it's just, I'm trying to make this concept make sense to you guys. So, f of r, say it's like r squared, okay? Then f of theta and phi, say f of theta and phi is like, I don't know, phi times theta cubed, okay? This means that r, then, is the square root of minus theta phi cubed. This implies that f is a function of the square root of minus theta phi cubed. But remember, f is purely a function of r. So if these two are equal to each other, that means that f, and they're not constants, that means that f is not a function of r. And f of theta and phi aren't functions of theta and phi, but we define them to be purely functions of the radius and purely functions of theta and phi respectively. So clearly, this means that f of r has to be a constant, and f of theta and phi has to be another constant, because we can get around this kind of paradox, not real paradox. We can get around this problem. Like, the only way to go about this problem is to make both of these constants, because if they're not constant, well, then they're not purely dependent on r, theta, and phi, and we made them purely dependent on r, theta, and phi, because remember, we defined the radial function and the angular function, these circular harmonics, to be purely dependent on r and theta phi, right? So this means that they have to both be constant to each other. Because if they are constant, then we can get around this. Hence we can say, oh, this is like, 3r to the 0th power or something. So we end up having technically still purely dependent on r, but it's a constant now. And r is just like raised to the 0th power. Same thing with f of theta phi. So if these are constants, well, then our problem is resolved. Basically what I'm saying here is that this has to be a constant, and this has to be a constant. So what constant are we going to make them equal to? Well, let's make the radial part, let's make that constant be L times L plus 1, where L is just any constant, it's just any constant number, is a constant plus another constant times another constant. It's just a constant, right? Let's let the angular part be minus L times L plus 1, so that this plus this will give us 0. Okay, maybe scratching your heads right now. You should be scratching your heads right now. Say, whoa, why are we making these be the constants? Why not say, oh, this is like C, right? And then this is like minus C, where C's a constant. Why I say it's L times L plus 1 and minus L times L plus 1 respectively? This is because putting it in this form is going to make a differential equation that we're going to solve in the near future much more easier to solve. So that's why I make this constant in this kind of weird way. This isn't like assuming anything, by the way. L is some general constant, therefore L plus 1 times L again is also another general constant. We're not losing any generality making this constant this instead of just like c or anything. Okay, so let's go back to this side. So what we have here now, I'm just gonna write the whole thing down again. Sorry for the crying baby right next to me. So this is 1 over r. It's 1 over r times d over dr of r squared dr over d little r minus 2r squared over h bar squared times v of r minus e, okay, plus 1 over, that's right, small now, 1 over y. This is a very big term. 1 over sine theta, partial theta, f sine, even smaller now, sine theta, partial y, partial theta, plus 1 over sine squared theta times second derivative of y with respect to phi. You guys can see that, I know that, here we have that. And then plus v, oops, wait, nope, that's just it. And this equals 0. Okay, this whole thing equals 0. Alright, so again, here we made this term, this radial term, with some constants here. We made that be L times L plus 1. And we made this term be minus L times L plus 1. Now you may be going, whoa, why is energy included in the radial term? Well, energy is a constant, so we can just we could put this in the angular term, but it's better to put this in the radial term. It's more easier because when we solve our equation for the radial wave functions, it's gonna be more easier to solve. It's more nicer if we put our energy in this left-hand term with the other radial terms. So this minus this is 0. Okay. What we've done is we have successfully separated our equation into effectively 2 parts. I really gotta do something about my stutter. So what I have now is I have 1 over r d over dr times r squared d big R over the little r minus 2mr squared over h bar squared times v of r minus e. This whole thing is just L times L plus 1, okay? And then similarly, 1 over y times, this and everything, 1 over sine of theta, partial over partial theta, of sine of theta, partial y over partial theta, plus 1 over sine squared theta, partial y, partial phi, is going to be minus L times L plus 1. This is where you say goodbye. Like, we say goodbye to the radial wave function. Because, like, we can do some further simplification by using change of variables. But right now, like, we're pretty much done with the radial wave function. Like, again, we can simplify this a bit, but it's no longer of any relevance to us. Because what we care about is the angular, we care about the spherical harmonics, okay? And to solve for what R would be, we'd have to actually plug in some potential. Remember, we have to plug in some potential to find R. Which we would do for the hydrogen atom, and just any potential we care about, we just plug that in and we find R. So we can't really do anything much else with this radial term. So you have to say goodbye to it. It's very important, but it's time to give the spherical harmonics a bit of shine today. So say goodbye to this radial term. We will not reference it at all for the rest of this video. Oh, except for the very end of the video. So what we care about now is the angular part, and we want to solve for big Y. Remember that, okay? So now what do? Well, now we can manipulate this equation so that big Y is solvable. So what I mean by that is that we can multiply both sides by Y. Okay, this makes this y go away. You can also multiply both sides by sine squared theta. Sine squared theta. So now when we distribute this guy inside, this becomes sine theta. And this becomes 1. So now we have, and this goes away, right? Now we have sine theta partial over partial theta of sine theta partial big Y partial theta plus, this is just 1, right? So plus partial Y phi equals minus L times L plus 1 Y sine squared theta. Okay, so that simplifies it a tad bit. So now what? Now what do we do? Well, now we can do separation of variables. So what we can do this for a tad bit. We can substitute Y of theta and phi into a purely theta dependent term B, and a purely theta dependent term pi. So remember, in the beginning, I kind of alluded to this. Oh, we could separate this into 2 parts, but that's not of interest to us. Well, now it's of interest to us, since we want to solve for Y theta phi. But once we do that, who cares about this? Once we do that, it's dormant. It's the same forever, for all the time. Even if the universe dies today, this term is the same thing. So now, so we can separate this into 2 terms. So to get those 2 terms, you can get this Y theta phi, and then we're done. So that's what we are trying to do now. Okay. Okay, so let's take a small 1 second break. All right. So let's begin again. So we have. So doing that, we now have sine of theta partial over partial theta of sine of theta partial over partial theta of b pi plus partial that of b pi again, right? B pi. I believe that should be that. And then this equals L times L plus 1 b pi sine squared theta. Oops, we should have done something else actually. I think. Wait, do we? Did we make one mistake? I'm just trying to see if I made any mistake here. I don't think so. I think everything is fine. Yeah. Everything's fine. Okay, I didn't make any mistake. Making sure. So now what do we do? Okay, so now, we just have this evaluated with the theta derivative. Pi is a constant. So we just move this to the front. Say pi to pi. Similarly, we do the same thing with this b over here. B, just move that to the front. Say pi to b. And yes. Okay, and now then we divide both sides by b pi over here. This makes this one go away. This makes this one go away. Now we get a 1 over pi term, then 1 over b term over here. So now we have 1 over b times sine of theta. Didn't sine of theta go away? Yeah. Sine of theta went away. It went by. So, yeah. Sorry. Because remember that we multiply both sides by sine squared theta. Right? Oh, no. It's still here. Okay. I was still right. Okay, never mind. Sine of theta is still here. It's just that this sine of theta went away to 1. So I have 1 over b sine of theta. Now what? So I have partial theta of sine theta partial theta of now this guy over here, and now plus 1 over pi partial big pi phi equals minus L times L plus 1. Okay. We then just add both sides by L times L plus 1. So this one goes to 0. And I have, you do the same, we'll add both sides by that actually. And I have 1 over b sine of theta partial over partial theta. A sine of theta partial this, that, plus L times L plus 1. Plus 1 over this equals 0. let's just use some brackets here. Here, this term is purely theta. Here was purely a function of phi. Now I paired L times L plus 1 to, I paired it with this because it's much more easier to solve this differential equation if we don't have any weird extra term tagging onto the way. However, if you have this term, we can use spherical harmonics to solve it. Okay, I'm just through the head right now. Sorry, just gotta stay awake. So now what we do is we make the same argument as last time. We have this is just equal to minus of this, right? So we have functions that depend on different variables being equal to each other, implying that these are constants. So this is just equal, let's define this to be equal to m squared, where m is some constant. This is equal to m squared, where m squared is again some constant. Okay, so they had to get to be 0. Okay, now what do we do? So now you have two equations that we have to solve. Yeah, this equation, that's 1 over b times sine of theta, partial of partial theta, of sine theta, partial pi of partial theta, plus L times L plus 1, equals m squared to solve. Now we also have the equation, 1 over pi, partial pi with phi, equals minus m squared to solve. This equation is very easy to solve. Like, you want to know this on the first day of DEs. So this equation, the solution to this is that pi of theta, pi of phi actually, pi of phi. Here, let me just write it again. Pi of phi. You can just tell what it is by the way it's structured. You can just tell at a certain point. It's going to be equal to ae to the I m phi plus be to the minus I m phi. And they choose a to be 1, b to be 0. Let m where negative to take the cases where m here has a negative next to it. And yeah, so you have pi of phi a, or it's just now e to the I m phi, where m, we got m right negative. So maybe wondering, wait, how do I know that this is a solution? I didn't solve it yet. Well, this is a classic differential equation, the harmonic oscillator from classical mechanics. If you guys want to see like a walkthrough through this equation, I recommend viewing my again I'm gonna reference. Oh, this is a different video. I recommend viewing my what's it called again? Yeah, the Schrödinger equation solution for a free particle potential. I show you guys how to solve this format of the equation, but for psi. And this is a k instead, and this is an x and stuff. So watch that video if you don't know why this is the solution, but after watching it, you should see why. Also, now what do we do? Okay, so our coordinate system, okay, draw it again. Z, x, y, okay, this is the Cartesian one, right? And then here we have, r, here I have theta, and here I have phi. Now, note that if we, so this is like this to this, right? That's a pi angle of rotation. That's to this over here. So phi and phi plus 2 pi is the same thing. Just because pi corresponds to like a 180 degree rotation, not 90, 180 degree. So 2 pi is 360 degrees, right? So phi plus 2 pi just brings you back where phi was at the beginning. This isn't something that we impose on our coordinate system. Rather, it is a natural property of our coordinate system. So phi of this phi equals phi plus 2 pi. So this implies that pi of phi equals pi of phi equals 2 pi. So they are the same, implying that e to the I m phi equals e to the I m times phi plus 2 pi. And this again implies that e to the im phi equals e to the im phi times e to the I should be doing this right. E to the I M. Slow run, right? Okay, good. So e to the I M phi times e to the I M 2 pi. Since this is I M phi plus I M 2 pi, and then that's the same as the product of these two exponentials. Okay, and this implies that this has to be 1 since this equals this, right? So e to the I M 2 pi should be 1. But now we expand that in terms of sines and cosines. So this is like these. It's just orders of identity. Remember that from trig or calc 2, I think. So if this can be like the big whole x term. It's the x analogous to the order identity. Like you don't have to call it x. You can call it any value you want, but it means so e to the I M 2 pi. That's just cosine of m 2 pi. Since like m 2 pi kind of serves as like one big term, right? Plus I sine of, I should really do 2 pi m, not m 2 pi. Yeah. Cosine of 2 pi m plus I sine of 2 pi m. Looks more natural. And that's e to the I m 2 pi, right? And this has to be equal to 1, right? So how can we make this equal to 1? Well, to make this equal to 1, we have to make m be an integer, okay? So m has to be like plus or minus 0, 1, 2, 3, all the way to heaven. Yeah, so why must m be an integer? Well, because if m is an integer, this property is satisfied now. Because remember that sine of n pi is 0 and n is an integer. And if m is an integer, well, m times 2 is also an integer. So you have sine of an integer pi and integer multiple of pi. And that's just 0, right? And the cosine of an integer multiple of pi is 1. So that will be satisfied. If m is an integer, but we might reject this and say, well, remember how we let m be any number that we wanted. M could be anything. Well, m could still technically be anything. Well, for our physical states that can actually happen, states that converge, m is an integer since this property has to be obeyed logically. Okay, so now what about this one? So we're almost done, guys. Only have to stay awake for a short moment. So you have to solve this equation. Though there isn't a short way to solve this differential equation. Wait. Okay, good. Yeah, so there's a short way to solve the differential equation. To solve it, you'd have to use the power series, and I don't want this video to be an extra hour long, so I'm just going to tell you guys the solution to this equation. The solution is that, wait. Because we made a big mistake here. Wait a second. Wait, I think we made a mistake here. Yes. This shouldn't be pi. Sorry. This should be b instead, not pi. It should be b. Here is pi. Here is b. My bad. I hope you guys don't bring me at the stake. So yeah, so this equation is you use power series. If you guys want to learn if you want the exact solve it, I recommend looking up Lagrange functions. The solution to this equation, this one over here, the top one, the solution, I'll tell it to you, is that b theta, I have like deja vu for some reason, because I recorded this 5 times so far. B of theta is equal to, it's equal to I have to get my table out. B of theta, it's equal to A times P PML cosine of theta. I guess we say, oh, this is so simple, right? Very simple expression, but it's not. It's very convoluted. PML here, it refers to the associated Lagrange functions. So into the associated Lagrange. I think that's how you pronounce it. Functions. Okay. And if you're wondering, PML that's defined as being minus 1 to the m times 1 over x squared m over 2 and d over dx to the m of p to the lx. Now p to the lx, this is why I let L be next to this. It's very nice. P to the LX, well, it's nice because, like, you know, it don't make my Harmonic equation any more complicated. So PLX, so yeah, we'll submit it that way so that it's matches the format of the Lagrange equation problem thing. So PLX is going to be 1 over 2 L factorial. I'm just telling us what this is. I'm not solving it. I'm just telling you from right off the bat what each term means. This is 1 over 2 L factorial. Yeah, it's very convoluted. D over dx to the L times x squared minus 1 to the L. This one is called the Rodriguez formula. Es un muy buen formula. Cringe for a second there. So that's that. And yeah. So those are what it means. So I want to give an example of this equation in action. Let's solve this equation for m equals 2 and l equals 1. So p21, well this is 1 here. So p1x, that's just 1 over 2 to the minus 2, 1 factor is 1. First derivative of x squared minus 1, that's just 2x, right? And 2x over 2, so this is just x, right? Now p of 2, 1, that's going to be equal to minus 1 to the 2, 1 over x squared times 2 over 2, that's just 1. Then you have the second derivative of x. Derivative of x is 1, second derivative of x is 0. This whole thing is 0. Okay? So that's an example of this thing in action. Then b of theta. Plug 0 in here. B of theta is 0. A that bothers some normalization constant that we get to normalize. Okay. So that's what we have so far. And now I want to emphasize something very crucial. Or no, wait for this page. So note that this this over here, this what's this called again? It's called the associated Lagrange functions, right? So this note that it's not this one, the Rodriguez formula. Note that it's nth order in the derivative. It's a derivative of nth order, okay? And here I have a derivative of the nth order acting on this function, or the function that is L order, okay? So if m is greater than L, note this, if m is greater than L, oh, by the way, L and m have to be integers, by the way. Just know that. That's how this equation is possible if m and L are both integers. So yeah, so if m is greater than L, then we have a higher order derivative acting on a smaller derivative. And a higher order derivative acting on a smaller order derivative will just yield 0, right? Like I give an example, when m was equal to 2 and L was 1, our function was 0, right? Like if I have, say, some second derivative, right, acting on the first order derivative of x, these are both first order, this is going to be 1, but this is going to be 0, right? So higher derivative acting on small derivative if that's always going to be 0. This implies that if m is greater than L, implies that b of L will be 0, which then implies that b of theta equals 0, which then implies that our wave function itself is 0. Hence our wave function, psi of r theta phi, that is r of r times b of theta times pi of phi. So this is 0, the whole thing is 0, right? So of course this means that for physical states m can't be greater than L, since like our particle, we want the cases where our particle actually exists. If a wave function exists, if the particle is there, then m ought to be greater than L. So that this whole thing is 0 once the value of the derivative. Okay? And so if m is greater than L, right, this is 0. Right? So this means that m has to be less than or equal to L for like real physical states that exist. So for example, if m equals 2, this implies that L can be, sorry. If L equals 2, this implies that m can be 2, m can be 1, m could be 0, and it could also be minus 1, and it could also be minus 2. Okay? Kind of ran out of room there. But yeah, it could also be minus 2. It just has to be smaller than L. If L equals 1, let's just give me a page here. If L was equal to 1, this means that m could be 1, but m could be 0, and m could also be minus 1. And there's a pattern here, right? There is a pattern here. The pattern being, like, oh yeah, so basically, sorry, I should mention that the absolute value of m has to be less than L. Not just m itself, absolute value of m. Because we can have minus 2 here, because the absolute value would be greater than L. So that's why. So we see that the values of m is restricted by the values of L. I should have said this earlier, but L is actually it's an integer, right? It's an integer when we solve the Lagrange equation thing. Like L comes out as an integer. No, when we first defined L, it could have been any number, and it still can be any number. But for the other numbers, our wave function diverges, and it's not physical anymore. So that's why we let L be natural numbers. Sorry, L can be integers, and yeah. So m is constrained on L. So the pattern here is that m is just like L minus 1. How do you write? Yeah, it's like L minus, say, L minus, say, how do you write that pattern again? Okay, yeah. So m is like minus L, and minus L plus 1, like so on, all the way to L. Okay, all the way to L. It could be any one of those values. And to be more precise, the possible values of m is just 2L plus 1. Here, for example, when L is done, we had 3 terms. Well, we just put 1, 2 plus 1 is 3. 3 possible values of m. Okay? And this, you might notice L is actually known as the angular momentum quantum numbers. And these are the states, the corresponding states that are eigenstates of the angular momentum operator in quantum mechanics. L hat, I think it's L2. I think actually, but and m is known as like azimuthal quantum number, by the way. So yeah. So we're actually almost done here. So this should be a brief recap. We don't know what R is. To get R, we have to solve the radial Schrödinger equation. But we do know what y of theta and phi is. Okay, so y of theta, that's just b of theta pi of phi. Pi of phi was just e to the I m theta, right? E to the I m. Sorry, phi, e to I m phi. And b of theta, remember that was just a b m l. This one over here. A p m l cosine of theta, right? So now we have to normalize this, actually. So how do we normalize this? So normalization just means that the integral of our wave function for like all the possible numbers is 1, essentially. I don't want to go too deep into normalization here because videos is already way too long. But basically, to normalize our wave function, we just have the integral of psi squared part differential is said r squared sine theta dr d theta d phi. That's our kind of our infinitesimal volume form. We make this a bit more simpler if you do some change of variables here and make this equal to r squared dr, but then make this whole term be defined as omega. So make it defined as sine theta d theta d phi. So now we have integral of psi squared r squared, and then dr, and then so this is defined as d omega. So d omega right here, and then we break this into multiple terms. We break this into the integral from 0 to infinity, since that's the value r can take, of r squared dr times integral from 0 to pi until 0 to 2 pi y squared d omega, since like theta can go from 0 to 2 pi, phi can go from 0 to pi, and this is 1. This term has to be 1. This term has to be 1 as well. But we can break this down into 2 parts. Remember, it could be b times phi. So it implies that b theta and phi there have to be normalized individually. And remember that b theta was like a times this term, a times the Lagrange polynomial times cosine theta. Those are actually polynomials. And so a is a normalization constant, and when we normalize it, we actually get this value for b of theta. We get that a should be like this big old convoluted term. Like we get the a should be like it's like a has to be like the square root of like 2l plus 1. It's a really long term, but once you normalize a, we plug that in. Once we normalize a, and you multiply that by p, and then cosine theta, and then multiply that by pi of phi, we then get what we call our spherical harmonics. And our spherical harmonics, once you normalize it, put it in b theta, then multiply that whole thing by pi of phi, our spherical harmonics, ml of theta and phi equal the square root of 2l plus 1 creating l over 4 pi l minus m factorial over l plus m factorial times e to I m theta times this. So you guys can probably see that this term was like the OGA. So this is the normalized A, okay? And yeah, we call this, like we are technically down here. These are our spherical harmonics, and they're called spherical harmonics because if we were to graph these whole things, you'd get actual spheres for like different values. Like these look like orbitals actually. And like that's why our wave function for hydrogenic orbitals look like this. These are these spherical harmonics, the y, m, l terms for different values of m and l. And l is contained by m, by the way. So yeah, they're called spherical harmonics because they look like spheres. So yeah, that's spherical harmonics, guys. next couple of videos, we will be analyzing the hydrogen orbitals. So yeah, that is all there is to. I can't find my spherical harmonics page, but yeah, that's really all there is to spherical harmonics. I hope you guys have an amazing day. Bye.